everyone. This is this is problem solving week 12, and we will be covering how to compute lengths of curves, how to compute surface areas, and then we will talk about integration by parts at the last part. So look at the first example, which is about computing lengths of a given curve. So let me emphasize the statement for you. But here, an expression for a curve. This is a nice curve seen here. It's an asteroid. It is called an asteroid. So we want to compute the length of this asteroid by computing the half of the first quadrant portion. So we just interested in the half of the first quadrant portion. So the length that we interested in is this portion, okay? Where the x component of this point is given as this number, 3 times square root 2/4, and obviously this is x equals 3. Okay, so how do we compute length? Before we start, I think I want to recall something to you from the lecture videos. So let's say we have a curve like this, and we want to compute the length of it from some point A to some point B on x-axis, okay? Let's concentrate on this portion. Can we compute the length over here? Yes, we can. There is a very nice way to do that by using integral. We have to choose some notation first. To do that, as I explained in the recorded lecture videos, we need to divide the length of this curve over this portion into infinitely many line segments, and we will be calling one of those line segments as ds. ds is the notation for an infinitesimal small part of this curve, okay? ds. It will be important for us. By the way, this curve is y equals f of x curve given in this structure, as it is given like that in the example. Okay, here our aim is to compute the length. Let's denote that with L. And of course, if I integrate this very infinitesimal small portion, ds part, you know, I divide it into infinitely many small line segments, and I denote them by ds, how can I sum them all up? Of course, by integrating ds, right? If you integrate ds from this point to this point on the curve, you will of course obtain the total length. So what about this? I mean, is there an expression for ds? Can we find an expression for it? Yes, it is possible, and we can do that in two ways. Either, okay, let me explain the details here. In the first case, you will consider we will consider the case where the curve is given in terms of x. In the second case, everything can be symmetric. So your curve may be given in terms of y like that. So if the case is like this, where y is given in terms of x, the expression for ds goes like that. 1 plus dy over dx, y is a function of x in this case, right? Y is a function of x, so dy over dx square root. Everything is happening inside the square root, and you will integrate it with respect to x. This whole expression is the expression for ds, where we are in this case, okay? Where the situation, the picture of the situation looks like that. In the second case, the curve is given with respect to y. So let me draw another picture for that. Let me try to visualize the situation for you. Here, your curve behaves like that. X equals g of y curve. And you want to compute the length over this curve from some point C to some point D on y-axis. So the roles of x and y are totally changed, symmetrically changed, okay? And you want to compute the length over here. So again, you will integrate ds, where ds is a very infinitesimal small length on your curve. But the only difference is at this point. Instead of taking x derivative of y, you will take y derivative of x. you see, you completely change the roles of x and y, and you will be taking the integral with respect to y. Okay, here, you will insert the boundaries for x, and here you will insert the boundaries for y, like that. Everything is with respect to x here. In the second case, everything is with respect to y. And you know, the pictures visualizing what's happening is like that. They are also symmetric. Okay, that's how we will compute the length. And now it's time to apply all those ideas to compute the length of this given curve. I mean, in the first quadrant, half portion. So y is given with this expression. Let's turn back to question. Back to example, let's say. Here, our function y is given by this expression. 3 over 2 over 3, minus x over 2 over 3. And then you take the power 3 over 2. So, you know, we will be using this formula, so I will compute x derivative of the given curve. So, first of all, of course, you will take this power down. You know how to take the derivative by using chain rule, right? You don't touch the insider part. You write it as it is, and then you subtract 1 from the power. Then you need to multiply with the derivative of the insider part. So what is the derivative here? The first term is gone as it is a constant, and then you will take the derivative of the second part, which is minus 2 over 3 x to the power minus 1/3, right? I subtract 1 from the power again. And then you have these nice simplifications. Then it is time to insert this first derivative expression to the length formula. Okay, let's do that. Length is 1 plus dy over dx squared. Dy over dx is computed here. I will integrate this with respect to x from which point to which point they are given in the statement. From this point to this point. You know, the situation is like that. 3 square root 2 over 4 to 3. Okay, let's insert our first derivative function to here. 1 plus, what do you see here, should be squared, okay? I will directly write the square of it. So what we have, 3, 2 over 2 minus x2 over 3. Square of this is to the power 1, you know. And then I have this part, times minus x to the power minus 2 over 3. You see, instead of 1, I write 2 because I squared it. I take the square of it. Okay, now it is time to do this multiplication, okay? Let's do that. By the way, you keep writing the boundaries every step. And these are all happening inside the square root. You should also be careful about that. So what do we have inside the square root then? Just do this multiplication. 1 plus 3 to the power this multiplied with this. Since there is this minus, I need to change this plus to minus, right? And then these two are multiplied. The powers are simplified. X to the power 0 is 1 minus minus is a plus. Yes. Something like that, right? And then let's see what we have. Okay. By the way, let me check the equation for the curve. It is with minus. You know, I think the derivative of the insider part is like that. Yeah, it's correct. I put it here. 1 plus square. Yeah, I did a mistake here. As I am taking the square of it, this minus should be plus. Okay, let's fix just that part. So since I am taking the square of this whole expression, this minus will be a plus here. That's why I also need to change the sign of this part. Minus plus, you see, it will be a plus. Not plus 1, but minus 1. Okay, then after simplifying these two, we can move on. with computing the integral, okay? So what we have here, I have this expression inside the square root. This can be rewritten as 3 over x, since there is this minus here, and both can be written inside parentheses of this power. Okay, like that. So 3 over x to the power 3 over 2 square root dx, where x runs from 3 square root 2 over 4 to 3. Okay, you know, this is a power function and I can easily integrate it. What kind of power is that? 3 over x to the power, you know, square 3 over 2 divided by 1 over 2. It is in fact 1/3 power. You can always eliminate the square root with this power. Okay, then the integral of this thing is 3 over 1/3 is a constant which can be written out from the integral. And then inside the integral, what I have this. Then time to take the integral. 3 1/3 x. How do you take power integrals? You add 1 to the power and you divide by the same power. And since this is a definite integral, I need to insert upper lower boundaries for x. And then you will insert 3, you will insert this number, take the difference, so that you will obtain this real number as a result, okay? This real number gives you the length of this portion of the curve. This is just the half of the first quadrant portion. How many of them in the whole curve? 1, 2, and since we have in total 4 quadrants, 8 many of L's gives you the total length, right? Let's write this down as the final line. Total length is 8L. So 8 times, this is what our L is. 8 times 9 over 4. This real number, which is, okay, 18, is the total length of the given curve. It is a nice curve, has this shape, which is called an asteroid. Okay, any questions about our computation and so on? If no questions, I want to move on with the next case, with the next example. In this example, there's another curve. This time our curve x is given in terms of y. And as you notice, the boundaries of the integral is also given in terms of y. So we are, in this case now, everything is with respect to y, so we will be taking the integral with respect to y by putting the boundaries for y from y as c to d. This is the case now. Okay, the situation goes like that. This is x equals g of y. This is a symbolic picture, by the way, not the exact graph of the given curve. And from 1 to 2, we want to compute the length of this curve, and here length is computed with this formula. Always length is given by integrating ds, where ds is a very infinitesimal line segment on your curve. And the formula for ds is chosen as this way, where x is integrated with respect to y. Take the square, put dy here, and insert y boundaries here. Okay, everything is with respect to y. Derivative, integral, everything is with respect to y. So now, time to compute. X is given with this expression, y to the power 4 over 4 plus 1 over 8 y squared. Dx over dy we want to find. So 4 comes down, y cubed over 4 plus 1 over 8 is just a constant there, y to the power minus 2. So you take minus 2 down, and then you subtract 1 from the power. So after doing the simplifications, you see that the first derivative function is given by y cubed minus 1 over 4 y cubed. Okay, let's insert this to here in our formula. So the length formula goes like, sorry. goes like this. From 1 to 2, 1 plus square of this expression. This is the first derivative function. And everything is happening inside the square root dy. Okay? 1 to 2, take the square. 1 plus y to the power 8 minus this times this times 2, which is minus 1/2, plus 1 over 16 y to the power, or this would be 6, I guess. I'm sorry, it's 8. So something like this. I took this power. I computed this power here, okay? Wait. I think okay, sorry. This should be to the power 3. Okay, and this should be to the power 3. So I think this is the correct version now. Okay, so like this. And then what we have here, 1 minus 1/2 gives us plus 1/2. Okay, it goes like y to the power 6 plus 1/2, right? Plus this. Now we need to find a way to get rid of this square root here. And we can do that. Surprisingly, this expression is a perfect square. We can write this as a perfect square. What is that? It is something like this, okay? So if you compute this square, you will find exactly this expression, okay? Then the integral goes like, this is inside the square root, so you can eliminate this square root with this to the power 2. Normally, you eliminate square roots of squares of functions in an absolute value, right? So let me show that here in a very quick recall. So how do you evaluate this? Normally, you need to put absolute sign. But here, look at the values of y. The values of y are changing from 1 to 2. They are all positive. That's why the absolute sign of this expression is always positive. So I can just remove the absolute sign. I can write this after evaluating square root on this square power. It is just the insider part without any absolute sign because the value is positive over this interval. So something like that. Now, this is a very simple power function. We can easily evaluate this integral. It is add 1 to the power, divide by the same power. Similarly, this is y to the power minus 3, add 1 to the power minus 2, divide by the same power. And then finally, we need to insert the upper lower boundaries for y. Insert 2 first, then insert y for y. Insert 1 for y, take the difference. At the end, you will find this real number as a result of the integral. This is the length of the given curve that corresponds to the part over 1 to 2 over y-axis. So this is the corresponding length of the given portion, okay, in the y version. Any questions about this solution now? So we applied length formula in the y version. Everything is with respect to y. We take the derivative with respect to y, and then we integrate the we integrated this expression with respect to dy. Okay, if no questions, I will move to this example. Find the surface area. Now, we will talk about how to find the surface area generated by revolving some curve around x-axis, or the story can be totally symmetric. I will explain soon. Let me start with a quick recall here, okay? So what's happening here? We have a curve given in terms of x like that, y equals f of x. And what we are doing is we are revolving this curve around x-axis. Revolve the curve, given curve, around x-axis, okay? So what will happen then? Something like this will happen if you revolve it around x-axis. You need to draw the very same curve infinitely many times, right? While doing the revolution. So here, the inside is empty, right? Inside is empty. We are just revolving the curve, not the region under it. Inside is empty. What we were doing last week was, okay, let me also recall what we learned last week. We were doing something similar. So we had a curve again, given by this expression y equals f of x. We were not just revolving the curve, but the whole region under it, okay, around the x-axis. So revolve the whole region. Here we were revolving the whole region around x-axis. So then we obtain a solid object, okay? What we obtained was not just the surface area, but the whole solid object with everywhere is filled up. So here, inside is not empty. Okay, so we obtain a solid object with no empty part inside. We obtain a solid object. So we were talking about finding the volumes last week. But here, inside is empty. We just have the surface area of it. The whole inside the part is empty. We can talk about the surface area, so we will compute the surface area here. Surface area, okay? So you need to compare to understand the difference of the topic for this week and the topic of last week, okay? So this is the difference. Now I can move to the details, how to compute the surface area. So what we have here is just the, okay, let me draw the picture again. We have this curve given by y equals f of x, and after revolving it around x-axis, something like this happens, right? We revolve it around x-axis, and we are interested in the surface area of it. How we can compute the surface area is the following. So remember this infinitesimal small line segment on the curve can be denoted by ds, and we will compute the whole surface area by dividing the total surface area into cylindrical strips like this. Very thin cylindrical strips we will think of, okay? So this is a very thin cylindrical strip on the surface area. You divide your surface area into such cylindrical strips, infinitely many of them you will think of. And then let's concentrate on just this cylindrical strip now. This is the radius of it, right? This part is the radius of it, and it is exactly given by the curve, f of x. And the height is given by ds on the curve. So if you cut this cylindrical strip out, and if you cut it up, you will obtain a very long, thin rectangle like that, okay? There is a rectangle like that, where where this part, the circumference of this circle corresponds to this side, 2 pi r, where r is given by f of x, and this side corresponds to just ds. That's why the area of this rectangle is 2 pi r ds. If I integrate this expression, the area of this rectangle from this point to this point on x-axis from A to B, this integration, which is a continuous summation, will give me the total surface area, right? So this is the idea behind that. I mean, the surface area, let me write this down, then I will comment on it. Surface area that we are interested in is given by the integration, continuous summation of the area of this very thin cylindrical strip, which is the same as the area of this rectangle, which is given by this expression 2 pi r ds. And after this step, the expression for ds can be written into two ways, right? Here we have two ways to go. Depends on whether your curve is given in terms of x or whether your curve is given in terms of gy. If we go on the first path, the integration takes this form. R is f of x, you know, and the expression for ds is the one that we know from also above. We use it in computing lengths. 1 plus, okay, let me show it first. So remember, I explained also this distinction between these two cases here, also for computing lengths. This whole expression, these are both the formulas for ds, which is explained in the recorded lecture videos. If you wonder where does this formulas come from, you can go watch the videos, lecture videos, but they are like this, either in this form or in the symmetric form with respect to y. And you can choose one of these forms in your example depending on the structure. So this is the expression for ds, with respect to dx, with respect to dx or with respect to dy. So I am directly writing those expressions here. So dy over dx can also be expressed f prime of x, you know, dy over dx is the first derivative of your function. Just to be consistent with my notation, I will be writing f prime square here. And in the second case, the radius r will be written in terms of y. And here, y derivative of x, normally dx over dy squared would be written here, but y derivative of x is the same as g prime of y, right? That's why I will put this version here, square. Here the integration is with respect to x, here the integration is with respect to y, where this is written for the radius. This is written for the radius, and in this case, it will be from a to b on x and on x-axis. In the second case, it will be from c to d on y-axis, okay? So this is the summary. Maybe I can also draw another picture for the y version to visualize what's happening. In the y version, so the curve is like that, given in this form, x equals g of y, and you are revolving it, okay? And you are revolving it around y-axis, not x, but y. And you put your cylindrical strips, thin cylindrical strips like this, where this is again is the height of the cylindrical strip, and where the radius is here. Where the radius is here, like that. And for some arbitrary y on the y-axis, the radius is just exiting point here, right? And that point comes from your curve. So exiting point is directly coming from this curve, which is given g of y. So that's why we are putting g of y for the radius in the second case, okay? So 2 pi r ds, and in the formula for ds, it takes this form in this metric case in terms of y, okay? So this part is totally coming from ds. So this is the summary of what's happening for the surface area. You have two ways to go. Be careful. If your curve is given in this form, you will use this version. If your curve is given in this form, you will use the second version, in which everything is with respect to y. So that's what's happening. Okay, let's apply these two formulas here. By the way, I think I skipped the first example while explaining the details. So let's continue with the first example, and then I will solve the second one for you. Okay, back to example. Here, our curve y is given in terms of x with this expression, square root 2x minus x squared, okay? This is the given curve between these two numbers on x-axis, 0.1 less than 1.5, okay? So the situation is like that. And so let me draw quickly some symbolic picture for you. I am revolving this curve around the x-axis like this. So I will be interested in this cylindrical strip, writing cylindrical strip on the surface area, where this is the S and where this part is the radius of it. And the radius is given directly by the curve f of x. So surface area is computed, I already explained all the details, is computed by this expression 2 pi r ds. The 2 pi r ds corresponds to the surface area of this cylindrical strip, which corresponds to the area of the rectangle, which is all explained here. Okay, and then now I will go from this first path because our curve is given with respect to x. That's why I will be using this form of the formula. For r, I will put f of x, and for ds, I will put this formula. F prime of x squared, okay? This is happening inside the square root dx. And the boundaries are from 0.5 to 1.5 on x-axis. That boundaries are coming from here, 0.5 and 1.5. Okay, now the rest is just computing things. Let's compute f prime, where f is given like that. Okay, what is the first derivative of this function? First of all, I take the derivative of the square root like this, and then I need to multiply it with the derivative of the insider part, which is 2 minus 2x, okay? If you simplify 2's, the first derivative function will look like this then. 2x minus x squared, okay? So this is the first derivative function. I will insert here the square of it, okay? Let's turn back to our integral computation. So from 0.5 to 1.5, what we have is 2 pi, just here write f of x, 2x minus x squared, and here insert the square of what you find here. 1 plus 1 minus x, 2x minus x squared square root dx, okay? This is what we have. And then I need to improve the computation here, right? 2 pi, 2x x squared, just write here over a common denominator. 2x minus x squared plus 1 minus x divided by 2x minus x squared. Instead of writing a big square root over here, I will write it separately for the numerator and denominator like that. And then I will have this nice simplification here. Also, let me see. Also here, I guess I have some simplifications. So what we have there is, then let me write them down again. So here inside the square root, what we have, I think we have minus x squared plus x plus 1, right? So minus x squared plus x plus 1. And I think this is 1 minus x squared, right? Okay, then this goes like 2 pi. We simplified these two, okay. And then, so what we have there inside the square root is 2x minus x squared by the way, I think I forgot to put the square of this expression here, because remember what I did there was directly inserting square of this expression. So maybe I need some correction here. Okay, so I guess here we have 2x minus x squared and square of it. So let me write that down as 1 minus 2x plus x squared. Yeah. And see, we have other more simplifications here. This is gone with that. These are simplified. So what I obtain is just 1 coming from here. So these two are also simplified. So we have just 1, nothing but 1. So it is just 2 pi dx from 0.5 to 1.5. And this is a very simple integral to integrate. Integral of 1 is just x, insert upper lower boundaries, 1.5, so the result is just 2 pi. This real number, 2 pi, gives you what? Gives you the surface area of the surface revolving this curve, y equals square root 2x minus x squared curve around the x-axis, okay? So that's the solution. Any questions? Okay, if no questions, before we stop, I want to solve also this example before the break, which is computing the surface area again, area of the surface, revolving this curve over this interval around y-axis, okay? So as you can see, the curve is given in terms of y, and we are revolving it around y-axis. This blue one is our curve. After revolving it around y-axis, you will obtain this brown surface area. It's a very nice picture. Now, to compute the surface area of it, I need to divide it into cylindrical strips like this, right? So this is the thin cylindrical strip that I am interested in. So for an arbitrary y here, on the curve, I hit this point and I look at the x component of it. So exiting point here is given by the expression of the curve, of course, 9 minus y square root, okay? And this will be the radius for me. Okay, so this expression, g of y, is the radius of this cylindrical strip. So the surface area goes like surface area, which is the brown parts on the picture, is 2 pi r ds. Now I am choosing the second path, x equals g of y path, remember? So radius is given by g of y. And then the expression for ds goes like g prime of y square dy. This is the cool formula. Now let's write the details. G of y is 4 times 9 minus y square root 1 plus, I will take the derivative of this expression. Let's do that here. So for 9 minus y square, this is g of y. So the first derivative of that function is 4 times 1 over 2 times square root itself times the derivative of the insider part, which is minus 1. So what is this? It is in fact minus 2 over this expression. Okay, the first derivative goes like that. And I will insert here the square of it. Directly the square of it will be inserted here. So 4 over 9 minus y. Directly the square of the first derivative function. That's what we have. The boundaries for y is given like that, from 0 to this strange number. Okay, let's put that. 0 to this number. 0 to the same number, okay? And here we need to write over a common denominator, 2 pi for 9 minus y squared. So what do we have here? 9 minus y plus 4 over this common denominator. Instead of writing a big square root, we can separate it into 2 parts for the numerator and denominator separately so that we can simplify these two. And then what we have? 8 pi can be written out from the integral. What we have is just this part. Square root of 12 minus y dy. And the boundaries, of course, sorry. Like this. How do you evaluate this integral? Of course, we need some substitution here. Let's call this part as u. 12 minus y is u. Then what is du? It will be minus dy. So if this is u, dy is minus du. And if we want to rewrite the integral, it is something like minus 8 pi square root u du. This minus comes from this minus here, minus du part. So how do you integrate it? Minus 8 pi. This is in fact u to the power 1 over 2. You add 1 to the power, divide by the same power. You know, normally we all, if you want to write the boundaries here, you need to transform y boundaries to u boundaries at this, from this line. Okay, these are the boundaries for y, and you can easily compute the boundaries for u by using this equation. Or instead of that, you can compute the integral without writing the boundaries here, and then you can turn back to your original variable, 2 over 3. Okay, what was u? Now I am turning back to the original variable. U was 13 minus y, 3 over 2, 3 over 2. U was this, so I did back substitution here. Back substitution. If you do that, you can now safely insert the boundaries for y, because now I turn back to the variable y here, right? So the boundaries for y looks like this. If you insert this number, then 0, and then take the difference, you will find a real number, and that real number will give you what? That real number will give you the surface area of this brown thing here. Okay, so this is a nice example visualizing how do you compute surface areas if the curve is given in terms of y. You see, everything is with respect to y here. Okay, so any questions about this solution where we computed the surface area? If not, I want to stop here.